Welcome back, ladies and gentlemen, to another video with Mr. Kenton. This is for AP Chemistry, and we are continuing our work with Unit 3 and looking specifically at solutions. And as we dive into today's video, I want to give a brief caveat for what we're about to look at. So we're going to be looking at colligative properties, and I just want you to know that the AP exam doesn't explicitly test colligative properties, but that doesn't mean that the information that we're going over is not useful. I would imagine that for any freshman level chemistry class that you take, that they would require you to be familiar with these colligative properties, which is why we're going to take some time to go over them, because I imagine that maybe these were introduced in honors chemistry, and if they were just introduced, they were just said, hey, these exist. And so I want to take some time for us to look at them a little bit more in depth. So that's really what we're going to be diving into, colligative properties and how those influence solutions. So now that I've said that, let's dive right into what we've got here. And so colligative properties, what they are physical properties of a solution that are going to depend on the number of solute particles that are present in the solution, but not necessarily the identity of the solute particles, right? So that means you could possibly have multiple solutes in your solution when you start dealing with colligative properties. Now, the colligative properties, there are 4 of them. There's vapor pressure lowering, there's boiling point elevation, there's freezing point depression, which each of those, they're pretty self-explanatory, but we'll dive into them individually. And then the 4th one is osmosis. And so from our perspective, you've probably seen osmosis in your biology classes. From a chemist perspective, we're talking about the net movement of solvent molecules through a semi-permeable membrane toward a solution with a greater concentration of solute particles. All right, so slightly different definition here for osmosis, as you've probably seen in biology. Now, like I said, we've introduced those 4 colligative properties. We're now going to look at each of them individually. So let's dive in. Let's look at vapor pressure lowering first. Now, like we mentioned on the previous slide, our colligative properties are going to depend on the quantity of solute molecules that we have. This is very prevalent, especially in freezing point depression and melting point elevation, right? And so lowering vapor pressure, what are going to be things, or how is vapor pressure going to be lowered? Well, if we think about it, a non-volatile solvent is going to reduce the ability of the surface solvent molecules to escape the liquid. Now, I want you to remember when we were talking about vapor pressure, when we were talking about phase changes in gases, vapor pressure is simply this equilibrium that we reach when the surface of the liquid is escaping, and then you have the gas particles that are going back into the liquid form. And so what this is communicating is that if you add in something that's non-volatile, something that doesn't evaporate readily or convert to the vapor phase readily, then it's going to prevent the surface molecules from being able to escape the surface of the liquid. That's what we're communicating here. Now, the amount of vapor pressure that your substance is going to be lowered by is going to depend on the amount of solute that you add. And we're thinking about this from the perspective, like looking at moles of substances, okay? So the more you add, the more the vapor pressure is going to be lowered. Certainly, that's going to only go to a certain point to where it's no longer going to have an effect. But the general trend is the more solute you add, the lower the vapor pressure is going to be. Okay, and so here we're taking a look at 2 different situations. So let's say that in the container that's on the left, what that's expressing is that you have only the solvent itself, right? And so the solvent by itself, its particles are allowed to escape. They escape, they end up pushing the bar in a manometer, and it exerts a certain amount of pressure. Notice that it's shifted the liquid farther to the right. When you have something like a solution, right? So what we have in the right container, notice that less particles have been able to escape. And so then as a result, the pressure is less because less of the particles have been able to escape into the gas phase. So here, this is showing us this situation where adding a solute to a solvent, forming a solution, changes the vapor pressure of that solution in comparison to the solvent. Okay. Now, this is all regulated and related through Raoults Law. And so Raoults Law communicates that PA, the vapor pressure with the solution, PA naught is the vapor pressure of pure solvent, and XA is the mole fraction of the solvent. Then you can figure out the vapor pressure of the solution, PA, with the following expression. You've got the mole fraction multiplied by the vapor pressure of the pure solvent, right? So this is, again, this is like an application of Dalton's law, which we're using for gases. We're using it here in the context of solutions. So notice that there are some similarities there. Now, when we talk about lowering vapor pressure, ideal solutions are going to be solutions that obey Raoults law, right? As we add solute, we see a lowering in that vapor pressure. Now, what we do need to recognize is that Raoults law is going to break down when the solvent, and solute intermolecular forces are greater than the solute-solvent intermolecular forces that are formed, right? So we're talking about, in our solutions, we're talking about situations where the intermolecular forces in the solute and solvent are weaker than the interactions between the solvent, solute. So for Raoults law to be true, the new intermolecular forces formed in your solution have to be stronger than what you had previously, right? And then we would say that we're dealing with an ideal solution there. All right, so that deals with vapor pressure lowering. Let's take a look now at our boiling point elevation. Now, from the definition, it should make a lot of sense as to what we're talking about, right? So boiling point elevation is simply communicating that when you add a solute to a solution, to a solvent, and you make a solution, it's going to raise the boiling point of that solution with respect to the solvent. Now, when we look at boiling point elevation, our goal is to be able to interpret phase diagrams for a specific solution. So, right, we introduced phase diagrams earlier where we looked at the solid, liquid, and gas phase of an individual substance, right? Well, now our goal is going to be to do that for a solution. Now, as we saw in the previous slides, that we noticed that a non-volatile solute lowers the vapor pressure of our liquid and ultimately gas phases, right? And so what that's going to do is it's going to lower the triple point and critical point on your phase diagram. And so if you're looking at the phase diagram that's been listed here, the curve that's in black would be the pure solvent, right? So this has no solute particles added to it. Well, the blue line is going to represent the solution. And what you should notice is that here was our triple point initially, here's our new triple point, right? Over here, and what you see is you've got a shift, and so you've got different temperatures and pressures at which the solid, liquid, and gas phase of this solution exist, right? And just examining this for a second, what you can see here is that your freezing temperatures are different for the solution than they are for the just the solvent. And the same thing is true for the boiling point, right? The boiling point, the normal boiling point was initially here. Now it's been shifted over. Same thing here. Your normal freezing point was at this given temperature here. Well, with the solution, the normal freezing point is now here. And so now let's look at what's really going on here when we're changing the boiling point of our solution. So with boiling point elevation, it can be related through an expression. And so with colligative properties, it's important to note that the units of concentration that we're dealing with are with molality. I know that was introduced at the end of the previous video. Molality is a form of concentration. And so when we read this, it says the molal boiling point elevation constant. Molal is just getting at that idea of molality. Kb expresses how much change in boiling point, delta Tb, changes with the molality of the solution, right? And remember, molality focuses in on the mass of your solute divided by kilograms of solvent, right? So big difference there, not dealing with concentration like molarity. Now, boiling point elevation can be determined using this expression right here, delta Tb equals Kb times m, right? So the change in boiling point equals the molal boiling point elevation constant times the molality of our solution, right? And likewise, freezing point depression. This is going to show us the decrease in freezing point. How we can calculate that is directly proportional to the molality. And what we see here, delta Tf, so the change in the freezing point of our solution, is going to be equal to Kf, which is the molal freezing point depression constant, times m, right? And for reference, you would never have to memorize any of those constants like Kb or Kf. Those would be provided to you in the context of a problem, if you were given one. All right, and again, bringing us back to our phase diagram, we can see again, we've got these changes in the freezing point, and we've got the changes in the boiling point. And then listed over here, there are several normal boiling points that are listed for substances, and then it gives their Kb and Kf values and how that expression would be influenced by the presence of a solute. And I know I haven't mentioned it here currently, but we think about practical applications for freezing point depression and boiling point elevation. One that I think is really important for us to consider would be something like the way a car functions. I'm sure you guys are familiar with antifreeze. And antifreeze is an important liquid in terms of the health and the functionality of an engine, right? Antifreeze prevents the liquids that are inside the engine from freezing. Why is that significant? Well, if the liquids freeze, typically what happens is that they expand. Well, if liquids expand in a solid forms and it expands within inside of an engine, it could cause the engine block to crack. And if that happens, the car no longer functions properly. So antifreeze is one of those things. What it does is it lowers the freezing point of the liquids that are moving throughout the car engine so that it can go to lower temperatures before it freezes. Likewise, boiling point elevation is going to make it so that a liquid is going to boil at a much hotter temperature. So in the context of a vehicle as well, right? It would have to be at a much higher temperature for the liquids to be vaporized, specifically the water, if you will, to be vaporized from the car, which would then in turn cause the car not to function properly, right? So it has some practical applications and even things that we deal with on a day-to-day basis. All right, and our last colligative property is osmosis. So like we said, osmosis is the movement of the solvent to a more concentrated place within, let's say you have two different concentrations that you have. That's what's going to take place, right? It's going to shift towards the side that's more concentrated. So in osmosis, eventually, what we know that's going to happen, there's going to be a shift. Like if we look at this tube, you've got a concentrated and a dilute solution. What's going to happen is that it's going to shift, the solution is going to shift, the solvent's going to move over to the side that's more concentrated. Now, eventually, that's going to stop. It's not just going to keep moving. Eventually, it's going to get to a point where it stops. And so the osmotic pressure, pi, is the pressure required to stop osmosis. And so what we're seeing here, the difference in the heights between these two levels, would represent the osmotic pressure, because no more solvent is transferring to the more concentrated side, right? And notice that in the diagram, there is a semi-permeable membrane that's only allowing specific particles to pass through. Now, osmotic pressure can be calculated as pi times V equals nRT. Well, if you just want osmotic pressure, pi, it's a form of pressure, is going to be equal to N over V times RT. And if you're putting your thinking cap on, you might be thinking, well, N over V, that's moles over volume. Well, if I have the concentration, that's just simply molarity times the ideal times the gas constant times T, right? So molarity times R times T will give us osmotic pressure. Now, when we talk about solutions, like what we're looking at here in this osmotic pressure scenario, you can have isotonic solutions, which means that you have two solutions with the same osmotic pressure separated by a semi-permeable membrane, right? Now, you can have hypotonic solutions. So what that's going to communicate is that you have a solution that has a lower osmotic pressure than a hypertonic solution, right? So hypotonic means that it has a lower concentration, right? And conversely, a lower osmotic pressure. Now, osmosis, I know we introduced this idea of spontaneity when we were talking about solution formation. Osmosis is a spontaneous process. Chemists don't have to apply any outside interventions to cause osmotic pressure. Like if we're looking at this container, chemists don't have to do anything to cause the dilute solution to move over. The only thing that needs to happen is there an ability for the solutions to interact and for the dilute solution's solvent to move over to the more concentrated one. Hope that makes sense. All right, and a specific application that we're going to look at from a biology perspective has to do with red blood cells. Because we think about it, red blood cells are surrounded by a semi-permeable membrane. And so that means water and other liquids, in theory, should be able to move in and out of the red blood cell. And certainly depending on the type of solution that the red blood cell is in is going to determine how it's going to respond to that particular solution, right? So let's kind of take a look at these specific biological applications. So there's crenation and then there's hemolysis, right? And so in crenation, so it's going to be our situation that's on the left, you've got a red blood cell that's placed in a hypertonic solution. So that means that the red blood cell has the lower concentration, right? And this is all relative to the intracellular solution that it's in. So that means there's a lower solute concentration in the cell than in the surrounding tissues. So what's going to happen, because of osmotic pressure, the solvent is going to leave the red blood cell. So osmosis occurs, water passes through the membrane out of the cell, and then what happens in crenation is the red blood cell shrivels up, right? So its shape gets distorted. So that would be an example of that function in that biological system. Now, the other side of this is hemolysis, which is where the red blood cell is placed in a hypotonic solution. So that means that the red blood cell has a higher concentration of the solute, right, of whatever solutes that are in the red blood cells. And so what's going to happen, osmosis takes place, osmotic pressure kicks in, and what starts happening is that the low solute concentration surrounding the red blood cell, the solvent moves into the red blood cell. Well, red blood cells are flexible. They are a little bit pliable, but eventually, if it gets too occupied, the pressure builds up too much, the cell bursts, right? And that would be problematic. If your red blood cells start bursting, that's not good, right? That's an understatement, right? Now, both of these things, crenation and hemolysis, we don't want either of those things to happen, right? And so that's why things like if you ever have been to the doctor or the hospital and they've had to give you an IV, it's really important that when the nurses and the doctors are putting that together, that they put together an isotonic solution that matches up with your current conditions inside of your body. And so it's just kind of a neat thing to think through about how we can apply this idea of colligative properties to the medical profession as well. And so nurses certainly have to be aware of, are the solutions they're placing and using, are they isotonic? Are they going to be helpful to the patient? And are we going to make sure that we don't create any other issues that we're going to have to deal with so that we can just focus on the current issue that maybe you're experiencing? All right. And I think this is going to be the last slide on colligative properties. You could think of other things that happens in terms of osmotic pressure. A cucumber that's placed in a sodium chloride solution is going to lose water and shrivel up and become a pickle. I mean, that's essentially the pickling process, right? You've got a limp carrot that's placed in water. It's going to become firm because water is going to enter the carrot via osmosis. All right. When you talk about the diet, the type of food that you take in, salty food causes the retention of water, right? Because what you're doing is you're introducing these salts into your tissues. And so what's going to happen is that the tissues swell because they're taking in the water. We think about water moving through plants through osmosis. You think of salt added to meat or sugar to fruit to prevent bacterial infection. And kind of what happens there, bacterium is placed on the salt, will lose water through osmosis and die. And then thinking of active transport. Active transport is the movement of nutrients and waste material through a biological system. However, keep in mind, active transport is not spontaneous. Energy has to be provided to the system in order for active transport to take place. So these are all other examples of osmotic pressure playing out. So I hope that makes sense to you guys. That's going to end this particular video on colligative properties. Thank you guys for watching this. I hope that this was insightful. If you do have any questions, don't forget, fill out the Google form and feel free to bring them up during class. I appreciate you guys and look forward to seeing you again soon.